Hello, everyone. Welcome. Let's wait a couple more minutes to get some latecomers to join before we start. But thanks for joining. Not sure why we have a lower number of attendees than usual, but you are the lucky ones. So you'll hear an amazing talk today. To remind everyone, this is the best of TVLSI seminar series. This is, I think, the sixth of the series. They are all available on the Circuits and Systems Society website. So if you Google, you can see all the recordings of the previous five. Today we are lucky to have very interesting. I'm actually, very eager myself to. Oh, okay. Maybe they were waiting to get in. So we have a few more. Um, the talk today is called Backside Active Power Delivery with Hybrid DC to DC Converter enabled by Amorphous Oxide Semiconductor Transistors. It's an across the stack kind of talk that talks a co-design of technology, devices, circuits. So it's very interesting. It's based obviously of a paper that was published in TVLSI. The presenter is the first author on the paper, Jungyoun Kwak. And Jungyoun received the Bachelor of Science in Electrical Engineering and Computer Sciences from UC Berkeley. He worked previously as an engineer at Samsung Electronics, and currently he's pursuing his PhD in ECE at Georgia Tech under Professor Shimeng Yu. His research, as you can tell from this paper, focuses on monolithic 3D integration and emerging devices for energy efficient computing and power delivery. So, Jungkyun, you have the floor. Please go on.
All right, thanks for the introduction. Hello, thanks for joining today's IEEE TVLSI webinar. My name is Jungyoun Kwak. I'm a PhD student in ECE at Georgia Tech, working with Professor Shimeng Yu. So today I will talk about backside active power delivery. We propose a monolithic 3D-dimensional hybrid DC to DC converter using back-end online compatible oxide semiconductor transistors in devices. So this work was published in IEEE TVLSI 2025. So here is the outline for today's presentation. We organized the talk into the four technical parts and a summary. Part one covers the motivation and background. We will explain why we need the active power delivery on the backside, compare the front side and backside power delivery networks, and look at what Intel's and TSMC have done with backside rails. Part two introduced the key building blocks, our indium tungsten oxide transistors, the high voltage superlattice, metal insulator metal capacitor, and our previous chip demo with a switched capacitor converter that converts 12 volt to the 6 volts. Part 3 explains why switched capacitor design alone cannot go from 12 to the all the way to 0.7 volts, and how a two-stage hybrid buck stage plus switched capacitor stage solve the problem. We also introduced the trade-off between the capacitor density and the breakdown voltage, which motivates the needs for the proposed hybrid DC to DC converter. Part 4 shows the simulation results. This includes the machine learning compact model, the full 12 volt to 0.7 simulations, the power loss breakdown efficiency curve, and benchmark comparisons. So the main question is, why do we need to move voltage converter from circuit board all the way to the backside of the chip? To answer this, we need to look at what's happening as technology node is advanced. A modern central processing unit or AI chips need about 0.7 volt as nominal operating voltage. But typically, the intermediate input voltage is set to 12 volts. That is about 17 to 1 step down ratio. Every bit of the voltage loss along the way wastes the power directly. In part one, we look at the three things. First, the power requirements and voltage conversion demands as technology scales. Second, why the front side power delivery network has physical limits. Third, what the industry has done so far, why is not enough without active voltage regulations. So AI and high performance computing workloads are pushing chip power into the hundreds of watts and beyond. The board gives 12 volts, but chip in a 3 nanometer or 2 nanometer process runs at about 0.7 volts. That is about 17 to 1 step down ratio in a single power domain. So every millivolt of IR drop along the power paths wastes energy and reduce the voltage margin for the logic circuits. As compute density grows, load current also grows, making this problem worse. Two specific problems drive the urgency of this work: the convergence loss in off-chip power management integrated circuits and the wiring between the power management integrated circuits and the chip adds more waste that cannot be fixed without changing the architecture as technology advances. The plot shows required power and transistor density over the years. The required power in GPUs has grown exponentially after ChatGPT came out in 2020. Both trends point in the same direction. The power delivery problem gets harder with every new generation. The key idea is simple. If we move the voltage converter closer to the load, ideally onto the backside of the chip, we shorten the power paths, cut IR drop, and get faster response. That is the motivation for everything in this talk. On the on the left side is the front side power delivery network. In this approach, all the metal layers, signal wires, and power rails are on the same side of the wafer, above the transistors. Power rails have to share space with signal wires because they compete for the same metal tracks. Power rail width are very limited. A narrower rail has higher resistance, which means more IR drop when current is high. Also, the current has to travel down through all the metal layers from the bump pad to reach the transistor at the bottom. This long vertical path adds resistance and inductance. On the right is the backside power delivery network. A separate set of the metal layers on the backside carries power only. Signal and power routing are kept apart, so each can be optimized independently. Power rails can be made very wide, which means less resistance, less IR drop, and better noise margin. The backside metal connects directly to the transistor source terminal through the backside power BS, creating a very short current path with less resistance and inductance. Right figure shows the IR drop map comparing front power back delivery network and backside power delivery network from 2022 VLSI conference. It shows the backside power delivery network with high density decoupling capacitor can significantly reduce the IR drop across the chip. Backside power delivery has already moved from the research into the announced product at leading chip companies. Intel has shown power via technology in the 18-angstrom process node, where the backside power rail connect directly to the transistor source terminal through the VS. TSMC has announced the backside power rail in their A16 process for high performance in AI and mobile chips. The cross-section on the left is from the Intel's published Power BI work. It shows how the backside metal contacts the transistor source terminal directly bypassing the front metal stack. Intel has reported less IR drop compared to the front side power delivery by employing the backside power delivery. The figure on the right shows the TSMC's A16 architecture, which combines nanosheet gate-all-around transistor with backside power rail. But, and this is a key point, both designs still use passive backside power delivery. The voltage is still converted uh, off-chip by a power management integrated circuit on the circuit board. The 12-volt rail still travel through the board to the backside of the chip, and step down to 0.7 happens outside. Our work takes the next step, put the voltage converter itself on the backside. Because the signal routing and power routing are decoupled in this architecture, we can place the voltage converter directly on top of the backside power delivery network. This removes the long power delivery path. We call this active power delivery. To do this, we need transistors and passive devices that can handle 12 volt and be made uh, below the 400 Celsius, which is the part 2 and part 3 cover. Let me explain the limitation of the passive backside power delivery and show the architecture we are proposing. The left figure shows the current industry approach, a passive backside power delivery network where the voltage converter stays off chip. The 12-volt rail traveled from the printed circuit board through the package and bumps before reaching the backside rails. This long pass adds resistance inductance, as I mentioned earlier, which limits the efficiency and transient response time. The right figure shows our proposed solution, an active monolithic three-dimensional converter placed directly on the backside layer. By moving the converter into the chip stack, the power delivery path shrinks from the millimeter to micrometer. One of the biggest advantages is area. An object converter takes board space. A 2D on-chip converters shares area with logic and compete for routing. Our monolithic three-dimensional integrated converter sits above the logic layer and uses backside space that is not used for logic, giving a large reduction in total footprint. This part introduced the three key hardware components from our priority work presented in the 2024 VLSI conference, the indium tungsten oxide power transistors, and the high voltage superlattice capacitor, and our previous chip demo that shows the both can be built together. This is an important foundation for the proposed hybrid DC-DC converter. The 2-to-1 switched capacitor DC-DC converter used in our design needs only 4 transistor switches and 1 flying capacitor. The circuit diagram on the right shows the switch positions left shows the switch positions in one phase. Flying capacitor charges in series with input supply. In the other phase, it gives charge to the output in parallel. The timing diagram on the left shows the two non-overlapping clock phase. In the charging phase, switch 1 and 4 closed and 2 and 3 open. Current flows from into the input volt through the flying capacitor, charging it to about half the input voltage. In the discharging phase, switch 1 and switch 4 open, switch 2 and 3 close. Flying capacitor connects in parallel the output capacitor and deliver the charge to the load. The ideal output is exactly half the input voltage. We use the 2-to-1 ratio because it is easy to demonstrate the functionality of the back-end line compatible transistors and capacitors. The left figure shows the challenge of the monolithic 3D integration. If we simply fabricate the new transistors on top of the existing front-end line silicon transistors, the high temperature process needed for dopant activation, which degrades the front-end line devices below. The right figure shows a thermal budget sweep from VSI 2015. The x-axis is annealing temperature in degrees Celsius, and the y-axis is the front-end line transistor performance, the temperature. The performance stays stable only when back-end line fabrication stay below 400 Celsius. Above that, the front-end line transistor will degrade. A widely known solution for the back-end line thermal budget is to use a transistor fabricated at low temperature, such as amorphous oxide semiconductor transistors. For example, left side shows our back-end line tungsten oxide transistor process flow. There are 6 steps, but all the steps use lower than 250 Celsius degree Celsius, which means it satisfies the back-end line compatible process. However, a conventional indium tungsten oxide transistor with gate-to-drain overlap can only sustain 3 volts before breaking down. The reason is the electric field. In conventional structure shown in the figure A, the gate electrode overlaps the drain region. The electric field concentrates at the gate drain overlap edge, and the peak field quickly reaches the critical limit of the material, causing early breakdown around 3 volt. Figure B is the proposed in the 2025 VLSI, shows our solution gate to drain offset design by pulling the gate edge back to the drain contact. We've introduced an gated buffer region between the gate and the drain. The electric field is now spread across the offset region rather than concentrated at the single point. The simulation color maps on the bottom directly compare the two cases at the same voltage. In the conventional design, field is bright red at the overlap edge. In the offset design, the field is distributed evenly, with no single hotspot. This is what enables a device to hold more than 12 volt at the drain, as we will see on the next slide. Now I will introduce the indium tungsten oxide power transistor. This is the transistor that makes our 12-volt converter possible. The left figure shows the two device structures. The left is the enhancement mode device, which is normally off. It turns on when you apply a positive gate voltage. The right is the depletion mode device, which normally on. It has a negative threshold voltage and can be used as a high side switch. Both devices are made by atomic layer deposition below the 400 Celsius, fully compatible with back-end line integration. The key structural feature is the asymmetric gate to drain offset region. Uh, on the right figure shows the IDVG curve. The x-axis is gate to source voltage in voltage, and the y-axis is drain current on a log scale. The E-mode device turns on the positive threshold voltage. The D-mode device is already on at the gate zero at zero gate bias and turned off a negative threshold voltage. Both shows clean switching with a high on and off current ratio, and both hold well above the 30 volts at the drain. The second key passive device is the high voltage superlattice metal insulator metal capacitor. We use it as a flying capacitor in the switched capacitor converter. The cross-section on the left shows the layer stack, alternating hafnium zirconium oxide and aluminum oxide layers, four hafnium zirconium oxide layers with aluminum oxide between each, about 36.5 nanometer total. The metal electrode on top and bottom complete the metal insulator metal structure. The hafnium zirconium oxide has a higher dielectric constant than silicon dioxide or aluminum oxide, giving a density of about 6.7 femtofarad per square micrometer. The superlattice structures spread the electric field across the multiple interface, pushing the breakdown voltage above 6 or 10. Like the indium tungsten oxide transistor, this capacitor is made below 400 Celsius. It is fully back-end line compatible and suitable for flying capacitor in 12-volt switch capacitor converter. The false-colored microscopic image on the left shows fabricate chip from our priority work. It shows the indium tungsten oxide transistor and metal insulator metal capacitor placed close together, confirming that both devices can be made in the same process. The maximum process temperature was below 400 Celsius. The photo on the right shows the actual test setup. The chip is mounted and connected to the input, output, and control nodes through the probe station. A pulse generator provides the non-overlapping gate drive signals. This chip is first monolithic three-dimensional switch capacitor DC-DC converter made from back-end line compatible devices at 12-volt input. The test structure directly confirms the device models and design approach that we extend to a hybrid converter. Here the figure A shows the schematic of the 2-to-1 switched capacitor DC-DC converter. It illustrates the input voltage path from the printed circuit board to the monolithic 3D dimensional switched capacitor DC-DC converter, which delivers intermediate voltage to the chip. Figure B shows the clock signal and output voltage waveform. The top and middle waves are the clock signal applied to each transistor in the switched DC-DC converter. We supplied a 10 kHz clock to the chip. Figure C shows the zoomed output waveform. The simulation and measurement results match each other, confirming the feasibility of the back-end line compatible DC-DC converter. Now we enter the part three. This is a highlight of our TVSI work, the monolithic 3D hybrid DC-DC converter. This is the main contribution of our paper. Part two showed that we have working the back-end line compatible devices and 2-to-1 switched capacitor converter. But a pure switched capacitor design cannot achieve 12 volt to the 0.7 volt conversion. We need, as the next slide we will show. Part three, answer the question, is there a better topology that can do this conversion more efficiently and in less area? So for that answer, a two-stage hybrid, we propose hybrid converters combining inductors and capacitor have been widely studied in priority works to reduce the charging charge sharing loss, lower voltage stress on switches, and achieve a high conversion ratio with compact passives. Both in the off-chip discrete implementation and on-chip fully integrated design in standard complementary metal oxide semiconductor or using power transistors. To the best of my knowledge, none of them address the back-end line compatible constraint or the operating 12 volt input. Buck converter step down from in our design, buck converter step down from 12 volt to 1.5 volt, then single switch capacitor stage takes 1.5 to the 0.75 volts. The buck duty cycle handles fine grain regulation to hit the nominal operating voltage. But to make this work, we had to solve the two problems: how to make a compact on-chip inductor below the 400 Celsius, and how to choose a capacitor for the switched capacitor stage with high enough density while staying within its voltage limit. The next few slides address both. A pure switched capacitor converter cannot efficiently achieve the 17 to 1 step down from 12 volt to 0.7 volt. This slide shows why in numbers. The diagram on the left shows the chain needed for cascaded 2-to-1 switch capacitor in series. Going from 12 volt to the 0.75 volt requires 4 steps. So 12 to 6, 6 to 3, 6 to 3 to 1.5, 1.5 to 0.7 volts. The efficiency drops with every stage added. If stage runs at 90% efficiency, let's say, 4 stages in series gives a total efficiency about 65%. This drops further because indium tungsten oxide power transistors have a worse figure of merit than silicon, so each transistor add more loss than ideal converters. So now let me briefly explain each topology before comparing them. Switched capacitor converter transfer the energy using flying capacitor and switches with no inductors. In a synchronous buck converter use a high side switch, low side switch, and an inductor. The high side switch connect the input to the inductor for a fraction of each cycle, called the duty cycle. The low side switch connects the inductor to ground for the rest of the cycle. The inductor averages the switch voltage, giving an output of duty cycle times V in. By adjusting the duty cycle, the output can be set to any voltage. The hybrid two-stage design can take the best from both. The buck stage handles the core step down from the 12 volt to 1.5 volts and provides continuous voltage regulations. The switch capacitor stage handles the fine step down from 1.5 to the 0.5 volt efficiently. Because the switch capacitor stage only sees 1.5 volts, its transistor can be smaller and have lower on resistance. The result is better efficiency and smaller area than either topology alone. Let me go through the two-stage hybrid converter schematic in details. The stage one is about converter on the left, the high side switch, and demo the indium tungsten oxide power transistor normally on, controlled by pulse width modulation signal. The low side switch is E-mode, indium tungsten oxide power transistor normally off, turning on during the freewheeling phase. Together, they form a synchronous buck converter. The switching node connects to the cobalt, zirconium, titanium thin film inductor, which filters the pulse width modulation voltage to the DC average. An output capacitor removes the remaining ripple. The duty cycle is 12.5%, set to give the 1.5 volts output from the 12 volts input. Two to one. Stage two is 2 to 1 switched capacitor converter on the right. Four standard indium tungsten oxide transistors from the switch network. To achieve the high power density, the switched capacitor stage needs a high density flying capacitor. Because the flying cap only sees about 0.8 volt peak, we can use a much thinner and denser film than high voltage superlattice used in our priority work. The next two slides explain this capacitor choice in detail. The key lesson from our priority work in 2024 VSI is that breakdown voltage and capacitor density are inversely related. As the thickness of the superlattice dielectric changes, you cannot get both high density, high breakdown voltage at the same time. This is the main limitation of the priority superlattice capacitor and is direct motivation for hybrid topology. The figure on the right is a bar plot. The x-axis is superlattice thickness and the y-axis is capacitance density in the femtofarad per square micrometer. As thickness decreases, density goes up, but breakdown voltage comes down. The thicker superlattice in our priority switch capacitor converter gives a high breakdown voltage needed for 12 volt operation, but keeps density low at about 7 femtofarad per square micrometer. The hybrid topology solves this by reducing voltage stress on the flying capacitor with only 0.8 volt across the switch capacitor stage. Flying capacitor are much thinner, higher density film become viable. The thin hafnium oxide capacitor reported at IRPS 2020 is the specific film we adopt for the switch capacitor stage. The right figure shows the transmission electron microscope cross-section image of the stacked metal insulator metal capacitor. This four-plate structure achieves a density of the 141 femtofarad per square micrometer, about 21 times higher than our priority superlattice capacitor. The breakdown is around 1.6 volts. At 21 times higher density, the same capacitance value needs 21 times less area, combined with 0.8 flying capacitor stress from the buck first stage. This film is the right choice for the maximizing power density in our switched capacitor stage. For the buck stage to work, we need an inductor. The key challenge is that conventional off-chip inductors are bulky and cannot be integrated in monolithic 3D stack. Our designs use a back-end line compatible thin film magnetic inductor that is only 15 micrometer thick, making it suitable for monolithic 3D integration. The figure on the left shows the inductor structure. Spiral core coil on the top of the cobalt, zirconium, titanium oxide, amorphous magnetic film. The film is made by sputtering at low temperature within the back-end line thermal budget. The measured inductance density is 130 nanohenry per square millimeter. with a quality factor Q of 14.5 at 10 megahertz. These values from APEC 2020, the 130 nanohelmi per square millimeter figure sets the inductor area in our design. At this density, the inductor is the largest single part in our converter. Um, we have another challenge and limitation in a hybrid DC-DC converter. The control circuits here sits on the active silicon interposer, not on the back end line or the near the indium tungsten oxide backside layer. The schematic shows two control blocks, a pulse width modulation generator with amplifier, error amplifier for the buck stage, and non-overlapping clock generator for the switch capacitor stage. However, we cannot put control circuits on indium tungsten oxide backside layer, as I mentioned earlier, because P-type indium tungsten oxide has very low hole mobility. The silicon interposer can embed these circuits with little extra area, just like a high bandwidth memory-based die. The adder amplifier measured the buck output voltage and compares it to reference. If the output voltage is too low, the duty cycle goes up. If too high, it goes down. The non-overlapping clock ensures the two switched capacitor pays are never both on at the same time, preventing shoot-through current from the input to ground. So one key constraint for any monolithic 3D converter is the physical height. Our target is to keep the full stack below the 1 millimeter, which is required for the fit inside the thin consumer electronics like smartphone and edge AI devices. If the converter layer is too thick, it becomes a bottleneck for the whole system. Let me walk through the layers and show how we stay within this limit. At the bottom is a printed circuit board, which supplies 12 volt and holds decoupling capacitors. Above it is the silicon interposer with the pulse width modulation and switch capacitor control circuits in the standard complementary metal oxide semiconductor or power transistors. Above the interposer is the back-end line converter layer with all the indium tungsten oxide power transistors, thin film inductors, and capacitors. The cobalt zirconium titanium inductor is the thickest part at 15 micrometer. Total converter height, including the interconnect, is about 46 micrometer. At the top is the front-end line logic silicon chip. Its 0.7 volt supply comes directly from the switch capacitor stage output through the backside power VS. The shortest possible path. The total stack height is about 0.92 millimeters below the 1 millimeter target. This confirms the design is viable for thin, mobile, and edge AI applications. Now we enter the part 4, the simulation result and benchmark. Everything we have described so far, indium tungsten oxide devices, capacitor, inductors, hybrid topology, control circuit must be confirmed through the simulation. So our compact model metal is data-driven. We measure the fabricated indium tungsten oxide power transistor by sweeping VGS and VDS from the 0 to 12 volt for both E-mode and D-mode devices, collecting about 3,500 data points per device characteristics. Data-driven approach is needed because no physical-based model exists for the high-voltage indium tungsten oxide transistors across the full 0 to 12 volt range. The standard models like a BSIM are built for the silicon and do not capture indium tungsten oxide bias independent behaviors. The plot shows IDVG curves. The x-axis is gate source voltage in voltage, and the y-axis is drain current on the low scale. There are several curves, each at the different drain to source voltage from low VDS up to 12 volt. The solid circuits are measured data from the real indium tungsten oxide power transistors. Dashed lines are model predictions. The matches is very good across the full voltage range from the deep subthreshold through turn-on region up to strong inversion, including at VDS equal to 12 volt. The right figure shows the capacitor and voltage curve, CV curve. The x-axis is gate voltage in volt, and the y-axis is capacitance in femtofarad uh, per micrometer. The model also matches the measured capacitance and voltage behavior well. Together, IDVG and CV matches confirm that the Verilog A model correctly captures both DC and AC characteristics of the indium tungsten oxide transistor. The right figure shows the transient waveform of the hybrid DC-DC converter. The simulation confirmed the stable 12 to 0.7 volt conversion using the full hybrid converter with machine learning validated indium tungsten oxide models. The x-axis is time and the y-axis is the output voltage in volts. The voltage settled close to 0.7 volt with about 40 millivolt ripple. The ripple can be further reduced with the multi-phase hybrid converter as is commonly done in the opti converters. The duty cycle is about 0.125, which matches the design target of 1.5 volt divided by 12 volts. We chose 10 megahertz as the switching frequency because it balances inductor size and switching losses. The pie chart shows where the power losses go at the peak efficiency. Knowing each loss source is key for identifying future improvements direction because the IW power transistors is just not mature enough yet. The switching loss is 38.1% of the total loss. Conduction loss is 35.7%. The bottom plate capacitor loss is 26.2%. The switching loss is the largest term because the indium tungsten oxide has a high on resistance. To carry the needed current, we need to make the device with large. A wider device has more gate capacitance, which means more charge move every switching cycle. The conduction loss comes from the indium tungsten oxide figure of merit, on resistance times area, which is much worse than silicon lateral diffusion metal oxide semiconductor. That's LDMOS. At this stage, um, in the indium tungsten oxide development. Bottom plate loss comes from the parasitic capacitance on the bottom plate of the flying capacitor. It switches every cycle and waste energy through the switch resistance. As indium tungsten oxide technology matures and on resistance and gate capacitance figure of merits improves, the both switching loss and conduction loss will decrease together. The bottom plate loss requires different approach such as capacitor structure optimizations or charge recycling. The efficiency versus load current curve shows the classic trade-off in the every switching converters. The x-axis is output load current in millimeter amp and milliamp, and the y-axis is efficiency in percentage. The curve has the typical bear-shaped curve seen in the almost every switching converter. At light load, efficiency drops as load current decreases. The dominant fixed losses, gate drivers, output capacitance chargings, and switch capacitor bottom plate losses stayed constant regardless of load. As output power falls, but these fixed losses remain, efficiency drops. At heavy load, efficiency drops as conduction loss grows with the scale of the load current. At very high current, this loss dominates and efficiency falls. The peak efficiency is where the switching loss and conduction loss are roughly equal. In our design, this happens about at 40 milliamps. giving a peak efficiency of 95.6%, and peak power density was 330 milliwatt per square millimeter. The benchmark table compares our design to the state of art. The second column is of-chip hybrid buck converter. It has high efficiency, high power density because it uses mature silicon with low on resistance, optimized passive components. But it is not back-end line compatible and sits off-chip on the printed circuit board, carrying all the deliberate path losses we discussed in part 1. The third to fifth columns are published on-chip switched capacitor DC-DC converter works, including earlier back-end line compatible design I just presented in part 2. These shows a lower power density because of line capacitor available within the back-end line limits have a low density due to thick high voltage dielectrics or lower input voltage. Our design has a unique position. It is the first back-end line compatible design that accepts a 12-volt input while achieving competitive efficiency, high power density, and an ultra-thin 0.92 millimeter stack height. The combination of the 12-volt input, the back-end line compatibility, 95.6% efficiency, 330 milliwatt per square meter power density, and under 1 millimeter stack height makes our work distinct from all prior designs. Okay, let me go through now the four main contribution of this paper. First, we propose the first design study of a multi-degree hybrid DC-DC converter for backside active power delivery. The hybrid use a buck stage and the switch capacitor stage to achieve 12 to 0.7 volt conversion in single chip stack, going beyond the passive backside rails that Intel and TSMC have announced. The second, we built the first design guideline for the co-optimizing back-end line active devices and passive components under 1 millimeter high constraint required for edge AI or mobile applications. The key insight is that using the buck first stage directly enabled the ultra high density thin hafnium oxide capacitor, which cannot be used at 12 volt input directly. Third, we built and confirmed a machine learning compact model for indium tungsten oxide power transistors. The multi-layer perceptron-based Verilog A model correctly matches measured IV data across the full 0 to 12 volts range for the both E and D mode devices. For force, our SPI simulation gives a peak efficiency 95.6%, a power density of 330 milliwatt per millimeter square, and total area was 0.87 square millimeter in 0.92 millimeter stack height. This shows that the backside power delivery can compete with off-chip intermediate voltage regulators or beyond. That's all for the technical parts of the talk. Thank you very much for the time. I also want to thank our co-authors, Sunbin Deng and Junmo, and Professor Sumandara, and my advisor, Professor Shimeng Yu. I also thanks the IEEE TVSI editors and reviewers.
Okay, thank you. Thank you. Very interesting talk. So we have time now for a few questions, and let's start with the questions that are already on, in the Q&A. So there are three questions actually from Giovanni, and do you want me to read them or you want to read them? And so the first question is for state-of-the-art backside power delivery networks. Would they still have power vias in addition to passive wires?
Yes, yes, they will have a power vias.
Okay. The second question, and maybe you should go to last slide, part 2. For simulation results of the monolithic 3D switch capacitor DC to DC converter in backside power delivery network, is it normal for the IC layout simulation results not to have transients? Not sure I fully um,
I
understand.
see.
Yeah, and I basically he says I thought all switch capacitor circuits would have such transient spikes on switch when switching.
The simulation research from the multi-switch.
So I think the question is about the fidelity of the simulation results and whether there are maybe some things that are being missed when you do the circuit simulation versus when you would have actual
Oh, yes.
measurements. Yes.
That's yeah. If I understand correct, thanks for the question. If I understand correctly, I mean, the audience are looking at the figure C. If you see the figure C, we have a smooth curve, transient curve in the simulation, but in our measurement result, we see some spike in between the regulations. But yes, this comes from the limitation of our measurement setup. So the short answer is we think this is noise from the external components because if you see this measurement setup and this if you see this number, we use a very small DC-DC converter since we have a very limited availability in our university fab. Also, we actually fabricate this at Georgia Tech. And so because we have a very limited capability, so we made a very small DC-DC converter. And if you think about this converter is very small, but other exponent components and wires, all the parasitics are actually pretty huge. So when we see some switchings, our interpretation was when we have some regulation, the converter itself is working, but we see some noises. I think maybe for the next tape out or next chip demonstration, we should find a way to we can decompose these kind of switching noises. But in short answer, yes, the measurement simulation is if imagine you fabricate this in the real industry product that I don't think we would have the same issue as we've seen from the measurement results. So this is noise. Yeah.
Okay. And the next question, and by the way, for the audience, please ask more questions in the Q&A. I don't think there is a way to ask questions verbally, so please put them in the Q&A. So is the multi-layer perceptron that you use for machine learning based prediction, which you use to compare with experimental data of die IC testing results, or at least SPI simulation results publicly available for others? And if not, how can we replicate your MLP prediction results?
Yeah, thanks again for this question. We do not have a publicly open source model for this specific device. But in general, there are like recently there are a bunch of papers. They use machine learning to develop the SPI simulation, the compact model. So I think you can use their framework to develop. But one key challenge is you may not have experimental data. Um, so at this moment, the power transistor, we do not have any publicly available model. Yeah.
Yeah. Yeah, I mean, this is a big problem in the engineering community, unlike the
Yes.
science community. So the scientific community is much better at insisting that, you have this concept of reproducible results. I think our
Hmm.
community is still behind, but, it's,
I
yeah,
agree.
it's
So
it's uh, it's a chicken
there,
and egg problem. Yeah.
yeah, there's a another reason why we have not make it as open source yet, because our group we have a bunch of our simulators and everything. We try to make anything possible robust enough to open source or post it on the GitHub. But the thing is, this power transistor, if you see recent papers, this work, this fabricate device is very early work. So it's the device was not like a mature enough. So every year or every 6 months, our group and our collaborators, they are improving their devices. So it's the what I have right now for the model is not the best yet. So I think at certain stage they may want to release the machine learning model or either machine learning model or they can be the physical based model, but they think they need to improve more and they need more time to make it robust. For example, they try to improve the reliability. Although I explained the functionality here, but reliability, if you think about it, you have to use like a tens of years, but that's not the case at this moment. So I think that's a ongoing active research topic. So we have not released any compact model for this specific devices yet.
Okay. I have a quick question. So, you do basically 3D integration, and I'm amazed by the high efficiency of your DC to DC. It's in the 90% kind of, but still that means that now you add another 10% more power in the 3D stack. And so I'm asking about basically thermal issues. So you are already, these devices are very much thermal,
Yes.
yeah. So yeah, can you make a comment on it? And it's not necessarily about what you are doing, but we keep adding things in the 3D structures, which is great.
Yeah.
But by doing that, we exacerbate the thermal problems of. So yeah, do you envision doing something extra, something special in addition to what you do otherwise for
Yes.
thermals?
Thank you for the great question. So actually, this is 2025 VLSI, TVLSI, and along the way, I actually published another paper in IEDM that's about the thermally constrained DC-DC converter. So in this paper, we did not measure the temperature dependency or the reliability. We just demonstrated, and then we adopt this device to demonstrate the hybrid converter. But after that, while I'm writing this TVSI paper, I measured the reliability and temperature dependence, and I developed the compact model for that and run the aging simulation. And within the thermally constrained system, so let's say the temperature, at least the first thing we can do is the silicon devices, the industry, they guarantee up to like 85 Celsius in general. So does this DCC converter works at 85 Celsius? So at that time, the answer was no. We the whole purpose of the research was we gotta improve more because the it's gonna be thermally coupled, and then it's getting worse in terms of the structure. So that's a one thing. So that's what I did in 2025, 2025 IDM. And the next thing in parallel, what we do is we are trying to measure the DC-DC converter experimentally, measure the temperature and how it changes, how the self-heating affect the other circuits and the or, up above or at the bottom. And then the authors from the Korea, I think I believe the another university, they propose something called the heat spreader layer. So you have let's say you have all the conventional design, and before you put in your converters, you fabricate something very good heat spreader. So it has a high heat spring rate. So and then you put your converter, and then they experimentally demonstrate once you put the good thermal conductivity layer, then you can remove the heat efficiently, and the performance of the converter and the front end line transistors they are ensured. So I think that's there are a bunch of the people worry about the thermal issues. Yeah, they try to solve the issue and then also quantify the what's the real problems.
Okay. So we are at time. So Shinfei, do you if you have any final question, brief question, or anything to say, you know.
Um, yeah, so I just had the final question. So you mentioned the reliability, and now because the thermal is also getting worse, and I assume the reliability of this device is, um, I guess, not at the mature stage that it can be kind of like commercialized and so on. So,
Mm.
do you envision like the reliability is going to be a big issue with all the consideration of thermal and so on?
Yes. First, the reliability. Thanks for the question. Reliability itself, the transistor reliability itself um, is not there yet. If you think about you imagine you do the silicon tape out, it's not as good as the silicon transistors yet.
Yeah.
Because I think the amorphous oxide transistor have their own weakness in they call maybe it's a short time to go over all the detail, but the channel if you have some byproduct, let's say the hydrogen inside of the channel, that can modulate the threshold voltage by a lot. And so the researchers try to actively looking for how they protect the channel layers so that way they can ensure the transistor itself. And then the another thing is, as you mentioned, if you let's say if you have the external heat sources, how the transistor will be changing apart from the self-heating. So that's only also another topic people investigate. Also, if you take a look, power transistor 2025 IDM papers, they improve the reliability by a lot. So, so by using the different geometry in the transistors, so they kind of encapsulate the channels. That's a key idea. So they try to protect the transistors from the outside byproducts. I think that can improve the product, the transistor in the end. So I think I hope that we have some bright future. So I want to believe that this can be commercialized and the technology can be transferred to industry in the end, like hopes next decade or so. Yeah.
Okay. Yeah, thank you. We are looking forward to your future work and to
Yeah.
solve all these challenges. Yeah, I think we are a little bit over time, and yeah, it's time to conclude. Thanks again, Jungyoun, and for your nice talk and for answering all the questions. And thanks all for attending this seminar. So yeah, please stay tuned for future webinars. Until now, thank you again, and yeah, have a good day.
Yeah.
Thank
You
you.
too.
Bye.
Thank you. Bye.